Dr. Sarah Chen pressed her phone against her calf, watching ripples dance across her skin from the massage gun. Through her camera, invisible truths emerged. "What are you seeing?" her colleague Marcus asked, peering over her shoulder. "Mysteries," she whispered. "The waves tell stories about what's beneath." She'd been obsessed with this idea for months. Each ripple carried secrets, how fast it traveled, how it curved, its rhythm and frequency. Together, they formed something called a dispersion relation, a mathematical fingerprint of everything hidden under the surface: muscle thickness, tissue stiffness, the layered architecture of fat, muscle, and bone. Traditional elastography required ultrasound machines costing hundreds of thousands of dollars, MRI scanners, and trained medical specialists. Sarah's method needed only a smartphone camera and physics. "Watch," she said, applying the shaker to a gelatin phantom they'd created in the lab. The surface erupted in concentric waves. Her algorithm extracted motion from each pixel, transforming the video through Fourier analysis. Spatial frequencies, temporal frequencies, all captured in a glowing image on her screen. "That's the observed dispersion relation," she explained. "Now comes the clever part." Her computer ran thousands of physics simulations, each testing different combinations of thickness and stiffness. Which parameters would create waves matching what the camera saw? The optimization landscape appeared, a topographic map where peaks represented good fits. "Structural similarity index," she said. "It treats dispersion relations like images and finds the best match." The algorithm converged. 14.3 millimeters thick, 14.1 kilopascals stiff. Marcus checked their ground truth measurements with calipers and rheometry. His eyes widened. "Sarah, you're within 1%. On temperatures." Every time, Visual Surface Wave Elastography recovered the true properties. The waves didn't lie. The real breakthrough came with the 3D leg simulation. Using anatomical data from the Visible Human project, they modeled realistic tissue over bone. Sarah's method swept across the virtual calf, estimating thickness as it changed from ankle to knee. "It's tracking the anatomy perfectly," Marcus breathed. "Even near the ankle where everything gets complicated." Sarah thought about the applications. Tumors change tissue stiffness. Could waves detect them early? Liver disease, muscular dystrophy, healing injuries, all left signatures in how waves propagated. But more than medical diagnosis, she imagined something revolutionary: home health monitoring. Regular people tracking their own tissue properties over time, catching problems before symptoms appeared. "There are limitations," she cautioned. "The waves we can see, the quality of the video, the accuracy of our physics model, they all matter, and we need the right characteristic numbers." She explained how observation length, sampling rates, and element sizes all had to align properly. "But the principle is sound," Marcus said. "Ocean waves reveal the seafloor's topology. Seismic waves map Earth's interior. Why shouldn't skin waves reveal what lies beneath us?" Ripple crossed the gelatin. "Every wave is a messenger. We just learned to read the message." She thought of earthquake scientists using surface waves to map underground structures, of geophysicists finding oil deposits, of all the hidden worlds revealed by watching surfaces carefully. Now that same physics could peer beneath skin, turning every smartphone into a medical device. The dispersion relation glowed on her screen, bright curves against darkness, each bend and arc encoding information about the invisible world beneath. Mathematics and medicine merged through the universal language of waves. We published it as Visual Surface Wave Elastography, she said. But I think of it as listening to what our bodies are trying to tell us, if only we know how to listen. Marcus nodded. When do we test it on real patients? Soon, Sarah said, her eyes reflecting the dancing waves. Very soon.